classic chemistry question. We got a reaction. We need to know how much product we're going to get. Although, since we're starting gases, liquids and gases next week, I figured we might as well do one involving a gas. So this is a decomposition reaction. We haven't really reviewed like what kind of chemical reactions there are, but you can probably, what do you think a decomposition reaction means?
The chemicals separate, or the solution separates into the original elements?
Not just, yeah, it separates, it breaks up. Not always into elements, though. Basically, it just means one thing gets broken down into other things. That's all. So one thing becomes 2 or 3 or 4, however many things. And in this instance, we have potassium chlorate, KClO3. And when it breaks down, basically you just heat it up and it releases oxygen. So actually it's a source of, this reaction is a source of oxygen. And one of the things that is used like on spacecraft and things like that, it's a decomposition reaction that releases O2 for the astronauts to breathe. So when we're dealing with gas, it's hard to measure masses, right? I mean, it's really hard to determine what's the mass of the gas in this room. What I can determine, though, is volumes. We can measure volumes of gases pretty easily. And so in this particular instance, at 25 degrees at 1 atmosphere of pressure, 1 mole of gas, and the cool thing, that means any gas, is about 22.4 liters. Okay, so that tells us if we measure 126 liters of gas, then we can figure out how many moles that is. But what's the very first thing we're supposed to do when we have a question like this? Before we do anything, what should we do?
Balance the equation.
Oh man, nailed it. Yes, that's the very first thing. Because as I said, chemistry professors by nature are evil people. And we will often give you a reaction and not balance it and not tell you. And so if we have a quick look at this, we can see that 2 of the elements are balanced, but 1 of them isn't. Which one isn't balanced? Which element doesn't have this? Oh, oxygen, right. We have 3 atoms of oxygen on one side, but we only have 2 atoms of oxygen on the other. So that's not going to work. So what should we do to balance those?
Try to get to where they're both like the same number.
Right, exactly. We need to have the same number of oxygen atoms on each side. So what's the best way to approach that, do you think?
Six.
Yeah, 6, exactly. 6 atoms on both sides would probably be the best way to do that. So how do we do that? How do we get 6 atoms on both sides?
Multiply the first one by 2, right? The KCl.
So our reactant, we multiply that by 2. And
then you multiply the other one by 3.
What other one?
O2.
O2. Yeah, so we put a 3 in front. So there's, oh, that looks very ugly. Right, so we put a 3 here. Now, are we done?
No.
No, how come? I mean, we balanced our oxygen, so what's the problem?
The potassium chloride.
You multiply by 2 on the right side? No.
Oh, so we need to, so our potassium chloride now we have 2 potassiums and 2 chlorine atoms because we put a 2 in front of the reactant. So now we have 2 moles of potassium, 2 moles of chlorine. Luckily, they're together, so we can just put a 2 in front of the whole thing. Now we just double check and make sure that everything is cool. So 2 potassiums, 2 chlorines, 6 oxygens. We're good to go. So now we can start. So what should be the first thing when we have a question like this? I always write down whatever information I'm given. So pretty much the only information I've given is that I've got 126 moles, 126 liters of O2. So what do I do with that information? Need to multiply that by something. What am I going to multiply that by? What units am I looking for?
Moles, right?
Right, I'm looking for moles.
So you would multiply 1 over 20. Well, 1 mole is equal to 22.4 liters.
Right, so I put 1 mole over 22.4 liters. That gets rid of my liters, and I'm left with moles of O2. So now that I've got moles of O2, what do I do next? So right now I have moles of one of these products. What do I want to relate that to?
Two grams.
Grams of O2? Do I actually need to know what the mass of O2 is?
No, the mass of the product.
O2 is the product,
Oh, I mean the reactant.
the KClO3, potassium chloride. Yes, I need to know what the mass of this is. But what do I need to know first before I can calculate the mass?
The ratio of that to oxygen gas.
Bingo. The ratio of moles, right? Because all reactions are dealt in molar ratios, not mass ratios. So I need to, first I need to figure out how many moles of KCl3 I have. So what do I, so I want moles of KClO3, and I want to get rid of moles of O2. So what do I put in the numerator and what do I put in the denominator?
2/3.
Right. So from the balanced reaction, we see that there's 2 moles of reactant for every 3 moles of the oxygen product. So that gets rid of moles of O2. So right now, if you see that the only unit we have left is moles of KClO3. So we're almost home. So what's the very last thing we need to multiply that by? To get our answer.
The mass of KClO3.
Which mass of it? My answer is actually going to be grams of KClO3. But what do I put here to get me this answer?
Molar mass.
That's right, the molar mass of KClO3. So which do I put on top? The molar mass or moles? Moles or grams go on top?
Grams.
Grams go on top.
Yep. So grams of KClO3 over moles. So here we would put the molar mass. So that gets rid of moles of KClO3, and we are finally left with grams. So you can look up the molar mass of KClO3 since we're not taking a test or anything. You just would put that here.
Can we do that tomorrow?
And so, yeah, I mean, this isn't due for a week. So I just was going over how to do it. So we would multiply 126 times 1 times 2 times the molar mass, and then we would divide by 22.4 times 3. And that will give us our grams of KClO3. So yeah, I just wanted to point that out. So this is how we set up all of these. You're going to get lots and lots of these sort of questions. Make sure when and I've seen this and looking at a lot of the workshops you've done already. Some people are doing a great job setting up these particular when they're looking at the unit conversions, setting up unit conversions, are really good at it. And other people are just, I don't know how they're getting the answer they're getting, and they just get an answer at the end. So I want to tell you that since you'll be taking your test tomorrow, you have to show your work. And so if you were to give an answer to this question and not show me how you got it, you're only going to get half the points available. Okay. On the other hand, if you show me all the work you did and you made a stupid mistake and got the wrong answer, you're still going to get like 75% or 80% of the points. So it is well worth your while to show me how you set up your solution and sort of take me through it. And this is the way I like to do it. It basically ensures that if you have the right units at the end, you must have done it properly. If every other unit canceled and the only one left is massive KClO3, and that's what the question is asking, then you must have done it right. Okay. All right. So what I'm going to do is we'll go into our different rooms. I'll come and join you, see how you're doing. Make sure you get someone's got a screen up, so you can all work together. And I'll make sure that you're allowed to share your screens. So let me take care of that right now.
Excuse me, is workshop 5, I know that's due next week, but those questions, are those also on tomorrow's exam?
I'm not saying they are, and I'm not saying they're not.
Oh, that's very evil of you.
I told you we're evil. No, but these are questions that we've dealt with already. We've already dealt with moles and grams, that sort of thing. Pretty much the only thing we haven't really spent a lot of time on is balancing equations. So I definitely want to help out with that. And basically the concept of limiting reactants. So that's something I want to talk about tonight. But all the rest of the stuff we've dealt with before. This isn't new information, right? Hopefully not.
Yeah.
Okay.
By the way, your electronegativity chart helped
Yes.
me for my microbiology exam today.
Really?
Yeah, he asked what the most electronegative element was out
Oh,
of 4,
you-
and
you-
oxygen was oxygen was the answer.
Options number 2.
No. He had a list. So like carbon,
Oh.
nitrogen, oxygen, and there was like one other element.
There you
And
go.
so yeah.
Yeah, there's really only 3 that I know. I know fluorine, oxygen, and nitrogen. And carbon and hydrogen. That's about it. Because really those are the main ones we use. All right. So I'm going to open up the rooms and I'll be coming in and checking in on your progress. You can share screens, so please do. All right. There you go. Oh, open. There we go. Okay, so hopefully we're all back together. I wanted to just address a couple things before we basically review whatever it is you want. I was really happy that most of you figured out how to balance this. This is called a combustion reaction. For a fairly straightforward reason, we're burning something, right? We are burning butane. And butane is a hydrocarbon because there's nothing but carbon and hydrogen. And when you burn a hydrocarbon, your products are usually water and carbon dioxide if you have complete combustion. So the trick to balancing these, I think most of you figured it out. I could have made it more difficult if I had put an even number in there, even number of carbons. The trick to balancing these is to balance the carbons first, because the carbon in the reactant only goes to one place. It only goes to make carbon dioxide. So that one you can balance pretty easily. So if there's 3 carbons here, you automatically have 3 carbons there. The next thing you do is balance the hydrogens, because again, the hydrogens only go to make one product, to make water. And so I have 8 here, so I need to put 8 there. And that means 4 waters. Now, the last thing you balance is the oxygen. And the reason for that is because it gets split in 2. It makes both water and CO2. So you add up the oxygens in both your products. So here I've got 4 there, and I've got 3 times 2, I got 6 there for a total of 10. And then, so I need 10 oxygen atoms. So I put a 5 there. So most of you did that. The tricky part is if I've got C4H10. Let's do that one. So if I have, so that is propane. So if I have propane, oops. Now, and it does the same thing. Oxygen, it makes oxygen, it uses oxygen to make water and CO2. So now I have 4 carbons. And I have 8, I have 10 hydrogen, so I need to make 5 waters. So now I add up my oxygens, and I have 5 here, and I have 8 there for a total of 13. So how do I make 13 atoms when I could only get them in 2s? Well, then I would put 13 over 2. But if we're dealing with atoms, I can't have that in my balanced equation. And so what do I do in this situation? I want to get rid of the 13 over 2. So what do I do?
7.5. I mean 6.5.
Nope.
No.
No, I
No?
can't have half.
Oh yeah. Because of
I
that,
can't
yeah.
have half a molecule. So there's no such thing as half a molecule. I need to have a
So-
whole number.
Do you just increase it more then?
How? That's the balance. That's exactly how many oxygen atoms I need. That is balanced. I just can't have half a molecule. So I can't make it, more. I can't change that to a 7 because then that's not balanced anymore.
I mean, you could just wait. Can't you just add more numbers to like the CO2 on the right, or like the H2O?
No, this is balanced. I
Oh
can't.
yeah, it's
change
balanced
anything.
already. Yeah.
Yeah.
I mean, if you did that, then you'd have to change everything up, but then that wouldn't make sense because it's already balanced.
So what do I do to get all whole numbers?
You round. I don't know.
Can't round. What's the easiest way to take 13 over 2 and make it into a whole number?
Turn into a decimal?
Nope, that's not a whole number.
When you multiply 13 and 2,
Yes, I multiply it by 2. So if I multiply everything by 2, then it balances. So I multiply that by 2. I multiply this by 2. I multiply this by 2, and I multiply this by 2. And now everything's balanced. So that's the trick. So sometimes you don't have to do that. If the hydrocarbon has an odd number of carbons, it works out pretty easily. If it has an even number of carbons, then it's a nightmare. So it's difficult. It makes it more difficult to do. So if you have that problem, if you're left with something like 15 over 2 or 17 over 2 or something like that, just multiply everything by 2, and then you have a balanced reaction, okay? So everyone figured that one out pretty well. So one thing I wanted, so the last question I wanted to do with you, because,
Sorry,
oh,
I
yeah,
just wanted to ask you, on all of these, most of these problems, you keep talking about an excess amount.
mhm,
What exactly do you mean by that?
that's what I'm getting to right now.
Oh, okay.
So when you do when you have a reaction, so here I'm reacting bromine, bromine, the liquid, with ammonia gas. If I don't have both of them in exactly the right amounts, the right balanced molar ratio amounts in my reaction, one of them is going to run out before the other one. And the one that runs out first is the limiting reactant, meaning I don't have enough of that to consume all of the other reactant. So one of them is going to run out first. And when one of your reactants runs out, then the reaction's over. It can't go any further. So if I tell you, I think when one of the questions I told you that one of the reactants was in excess, that, like, for instance, if bromine is in excess here, that means the amount of product is completely dependent on the amount of ammonia. And that the moles of ammonia will be converted to moles of product, and that's it. And I'll have bromine left over. But right now, we don't know which one of them is limiting. We need to figure that out. So I'll show you how to do that. So what's the first thing we do in this sort of, I keep harping, what's the first thing we do for this sort of reaction?
Make sure it's balanced.
Make sure it's balanced. There's a lot of big numbers here. So bromine is balanced. We have 6 there, and I got 6 there. And hydrogen, I've got 24. And hydrogen, 6 times 4, 24. That's okay. And nitrogen, I've got 8 nitrogens there. And 6 times 1 is 6 plus 2. Yeah, so that's a balanced reaction. All right, so we got a balanced reaction, so we don't have to worry about that. So if you get a problem like this, you need to figure out which one is the limiting reactant. How do you figure, how do you think we're going to do that? How do we determine which one of these two is limiting? Think about what the definition of a limiting reactant is. What does it mean to be limiting?
I'd love to learn a trick for it. The way that I did it was I
Okay.
took how much I had of one element and I saw how much I needed of the other to react fully. And if it
Mhm.
was greater than or less than, I knew that the one that was less was my limiting, because I wouldn't have produced enough.
Oh, I see. So you reacted this, you figured out moles of bromine and moles of ammonia, and you figured out which one got consumed, which one you needed more of?
Yeah, I'd love to learn a quicker trick though.
Okay, that works. I'll just show you how I do it, and maybe we'll get the same answer. But what does it mean to be the limiting reactant? If the reactant is limiting, what does that tell you about the amount of product you get?
It's going to be determined by the one that you run out of first.
Right. So if I take that amount of bromine and convert it to product, and I take that amount of ammonia and convert it all to product, which one is going to be less? Which one is going to give me less product? Would that be the limiting reactant or the excess reactant? The one that gives me less product.
Limiting.
Limiting one. That's right. So that's how we figure it out. We convert all of our bromine to product, and we convert all of our ammonia to product. And whatever number is smaller, that's the limiting reactant. So we'll do that. So we've got 60. So the first thing I need to do, I got 67.9 grams of bromine. Oop, and I want to convert that to moles. Moles of bromine. And bromine is pretty heavy. It's 159.808 grams per mole. Then I want to figure out how much product is that going to make. So, and this is the cool thing. It doesn't matter which product you select. You can pick this one or you can pick this one. Doesn't really matter. I picked N2 because it makes the math a little easier. So I'm just going to figure out how many moles of N2 get made. So here I use my balanced equation. For every 3 moles of bromine, I make 1 mole of nitrogen. So that's 1 mole of nitrogen for every 3 bromines. And then grams of bromine, moles of bromine, and I'm left with moles of nitrogen. So I just need to calculate moles of nitrogen. And the moles of nitrogen that I would make is 0.5665. And I don't need to round anything yet. I just want to see what number is bigger. So next I go to ammonia, and I got 24 grams of ammonia. So before I go any further, I want to point out that a lot of students make the mistake of assuming if one mass is less, then that means it's limiting, and that is not true, right? You have to do this reaction. You have to do this calculation first.
So what you're saying is most people would, well, some students assume that because 24 is smaller.
Yeah, there's a lot less ammonia. What's the
67,
limiting reaction? Well, it's got to be ammonia, right? But maybe it isn't, because ammonia is a lot smaller. It's a lot lighter than bromine. So molar wise, maybe actually you have more moles of ammonia. So let's figure it out. So I want moles of ammonia. And the molar mass of ammonia is much smaller, 17.031 grams. Now, for every 8 moles of ammonia, I only make 1 mole of nitrogen. So then I get grams of ammonia, moles of ammonia, and I'm left with moles of nitrogen. And that number is 0.7046 moles. So that tells me if I use up all my bromine, I make that much product. If I use up all my ammonia, I make that much product. I make less product if I use up all the bromine. That means the bromine is limiting. So you just write down bromine is limiting. Bromine is. So the next, so does that make sense to everybody? Limiting just means you're going to make less. It determines how much gets made. That means if I have actually 68 grams of bromine and 24 grams of ammonia, that's how much product I'm going to make. I can't make any more because the bromine is going to run out and then I'm going to have ammonia left over. So then once one of your reactants is gone, reaction stops. So does that seem clear to everybody?
Yeah.
Okay.
I just want to make sure though, but okay, you canceled the grams of the bromine to the grams of the bromine, and then the moles of the bromine to the moles of the bromine. But aren't you just left over with what N2 is, not what bromine, the elemental bromine is?
So what's the question? I mean, I'm out. I've converted all the bromine. All the bromine's gone.
Yeah.
And I've converted it to nitrogen.
So is it nitrogen that is the limiting reactant?
Nitrogen is not a
Because-
reactant. Nitrogen is a product. So the question is, which,
Okay, it's just I
which
was just
one
thinking-
makes less product? That's the question.
Okay, so the answer would still the 0.5665 moles of nitrogen.
Mm-hmm.
That I mean that I guess I'm just confused because nitrogen, the product is nitrogen,
Right.
but the answer is bromine would be a limiting reagent.
Well, the answer being nitrogen tells me how much product is made. So that is all I'm interested in knowing is how much, when I react all the bromine, how much product do I get? When I react all the ammonia, how much product do I get? And so we pick one of the products. You can pick the other one if you like. It doesn't really matter. I just picked nitrogen because I just figured the math would be easier. So all the bromine converted to product makes this much. All the ammonia converted to product makes this much. The bromine makes less. So by definition, it's the limiting reactant.
Okay.
So that's all the information you need for this particular part of the question.
Okay.
Which one makes less product? So you just show, and you don't need to convert it to grams either. I don't care how many grams of nitrogen there are. I know if there's fewer moles, well, yeah, duh, there's fewer grams too. I don't need to know that information. I just which one is more. So if you have moles, that's enough information to tell you which one's more. But hold on to the moles because you're going to need them for the next part of the reaction, next part of the question. The next part of the question is super mean. What's the mass of the excess reactant that's left over? Well, we know that the excess reactant is the ammonia because all the bromine's gone. So how are we going to figure out how much is left over? We go back to the last part of the question and we see how much product got made. That will tell me how much reactant was used. And so I just subtract the starting amount from whatever amount was used, and that tells me how much was left over. So I'm going to need this number. I'm going to need the amount of moles of nitrogen that were made. So I go back to the previous question and I see it was 5.566 moles of nitrogen. That's how much was made. Now I convert that to moles of ammonia because I want to know how much ammonia was used in making it. And we can see there's 8 moles of ammonia for every 1 of nitrogen. Then I want grams of ammonia. So here I use my molar mass. And the molar mass of ammonia was 17.031 for every 1 mole of ammonia. So moles of N2, moles of ammonia. I'm left with grams of ammonia. So how many grams of ammonia is that? Oh, work it out. So 0.5665 times 8 times 17.
I got 77.184.
Yeah, I screwed this up. Oh, wait a minute. That can't be right.
I got it 77.17996.
Yeah, what did I do wrong here?
I think it's the mass of the.
Yeah, you put the mass of
should
the
be-
of the smaller one instead of the ammonia one, right? Shouldn't it be what do you call it? Let me go up 0.77046 instead of 0.5665
No,
because that was the excess one, correct? Because ammonia is the excess and
No,
bromine.
that's the limiting one.
Oh wait, ammonia is the limiting?
No, nitrogen, I'm sorry, bromine was limiting.
Yeah, bromine was was the limiting one, right? But it says the excess. What is the mass of the excess reactant? And I think the excess reactant here would be ammonia, right? So wouldn't we take the moles of N2 from the ammonia one instead of 0.5665?
I think, Professor, you multiplied it to 17.031. It should be 17.0031
Yeah, it shouldn't matter though.
for the mass.
Something's messed up.
I solved it a completely different way. But I got a completely different number. So
Yeah. Okay.
is the answer anywhere close to 4.77?
Yeah, that's what I,
That's what you've got? I can
yeah,
show
that's
how
what
I
I,
did it.
but now that I'm looking at the way I did it before,
I tried to keep it as simple as I possibly could without, going too far the other direction. And
I think the problem was, yeah,
Most of any
no, I screwed up the first part because I actually didn't balance the equation properly. Let me go back. Yeah, let's start over because I screwed up the original. All right, so let's go back one. Can I go back one? There we go. All right. So that much, I messed up the equation. I balanced it wrong. That's how I screwed up mine. So 67.9. I just want to double check and make sure everything is balanced now. Yeah, okay. So that's 1 mole of bromine and 159.808 grams. And for every 1 mole of nitrogen, there's 3 moles of bromine. So I think that was yeah, that's the problem I had last time. So 67.9 divided by 159 divided by 3. Yeah, now I get a different number, 0.1423 moles of N2. Now, do the same thing with ammonia without screwing up this time. So 24 grams of ammonia times 1 mole of ammonia over 17.031 times 1 over 8. Yeah, I had stupidly put a 4 here when I was balancing, forgetting that there is nitrogen there. So that is why I screwed up the first time. So see how easy it is to mess up the balancing of these reactions. So 24 divided by 17.031 divided by 8. 0.1762 moles. So this still is limiting, but the amount is much, much less than I thought. So that makes sense. So that is the amount of product we are going to make. So to figure out what the mass is, we now figure out if I make 0.1423 moles of nitrogen, how much ammonia did I use to make it? So I want to convert that to moles of ammonia. So that's 8 moles of ammonia over 1 mole of N2 times how much grams of ammonia is that? 17.031 molar mass of ammonia over 1 mole of ammonia. So we should get a much different answer this time. 14 times 8 times 17.031.
Excuse me,
Oh, yeah.
since the limiting reagent is whatever the number is for bromine, the smaller number.
Yes,
Why, I would think you would use, because it's excess reactant for question B, I would think you would use whatever is the higher number.
yeah, I am. That's what I'm figuring out. I'm figuring out how much ammonia was used in the reaction.
But wouldn't you use 0.17 instead?
No, because that could never be made because bromine is
because
the limiting reactant. So the most amount of product that could be made is this much because the reaction stops. When all the bromine is used up, the reaction stops.
Oh,
So bromine would have made this much. And so since it's limiting, that's how much gets made. That's like the definition of limiting reactant. So what I'm
Okay.
doing now is figuring out, okay, this is how much product was made. How much ammonia was used in making it? Because I know how much bromine was used in making it, 67.9 grams, and then it's all gone. So there's none left. But there's ammonia left over. The question is how much ammonia is left over? Well, to answer that question, I know how much was there at the beginning. I don't know how much is there at the end, but the difference is going to be how much was used in the reaction. And this answer is going to tell me how much was used in the reaction. So that many moles of product times this molar ratio of reactant to product, and that's the molar mass of my reactant, says that 19.388 grams of ammonia was used in the reaction. So if I have 24.0 to start with, and I used up 19.388 grams in the reaction, then the difference is what got used up. And so I would have that many significant digits. And the answer is 4.61 grams. So that's how much would be left over. So I started with 24. I used 19.388 in making the products. So the difference is 4.61. That's how much would be left over. Okay. So there'll be a lot more of these questions to come. That's basically how you do that.
Okay.
Figure out which one makes less product. It doesn't matter which product you pick, either one, doesn't matter. Whichever number's less, that's your limiting reactant. And the other one, so that's going to be all used up. There'll be any left. And whatever the other reactants are, if there's like 2 or 3 or 4 of them, they'll be left over.
I have a question.
Yeah.
I thought the chemical reaction that's listed above, like considered a reaction. I thought it was all like it's already balanced.
It is. Yeah,
Oh.
I stupidly didn't think it was.
I was like confused. Yeah.
Yeah, and I didn't notice that there was nitrogen there. I looked right past it.
I did the same thing.
The brain sees what it wants to see. So I saw, oh, there's eight nitrogens there. There's got to be 8 nitrogens there. Yeah, see, it's easy to make. See how easy it is? Aren't you?
Yeah.
You're so lucky to have a stupid professor who shows you how easy it is to make these mistakes. So then you don't have to make them. I make them for you.
good thing
All
you're
right.
not doing what your wife does. You make a mistake like that on medication. Oh boy.
Well, I definitely double check before you make that mistake on a clinical trial, you're in big trouble. So were there any other questions from this set before we basically just throw it open to whatever you like?
I solved it a little bit differently, and I was just
Okay.
wondering if it's
Did you get the same answer?
legal. I did.
There you go.
Can I show you or?
Sure. You want to share your screen?
Yeah, I can.
Okay. I will stop. Go right ahead.
So how I did it was I first figured the molar mass of the 2 that I was concerned about, and I figured how much I had in moles of each of those for the given quantities. Then
Right.
since it's a balanced equation, instead of even looking at the product side, I only looked at the reactant side since they need to match up. So that's this
Ooh.
part.
Oh, I see what you mean. Yeah.
So I took how much I had of the bromine, and I would need 1.13 moles of that in order to be fully reacted, which was less than this number.
Yep.
So I knew bromine was my limiting. And so then I took how much I had, which was that number, minus how much I used to get the difference, and then took that times the molar mass to get
Yeah,
the
that's certainly a
answer.
lot easier, isn't it?
That's why I thought maybe I did something wrong, but
No,
okay.
no, that's perfectly fine. That's perfectly fine. No. Beautiful. I mean, I steal from my students all the time. We came up with the Maria method of balance of making Lewis structures last night. So I'm going to be using that from now on. So I may use the Sonia method of limiting reactants as well. I just think that we just teach it that way because we want to drive home the point that it determines how much product is made.
Right.
So yeah, so the only difference is, yeah, I went ahead and figured out how much product was made, and you didn't bother because you didn't have to. So yeah, no, that's genius. That's great.
Okay, so then I did have another question here on the balancing of this equation, where when we did the class together, I also started by balancing the carbons, you know,
Yep.
and then looking at the hydrogens. And once I knew that my limiting one was there, then I just worked backwards. And so my coefficients were totally different. What was the correct answer for 3A? I was just wondering if I got it right or if I need to rework this.
Oh, you wondered if you're balanced? No, you balanced it properly. But I don't know what was the question?
Well, when we did it together in class, I think it was 13/2 for oxygen.
Oh no, that was for C4H10.
Oh, okay, that's why I was confused.
No,
Okay,
I was showing, yeah, if the hydrocarbon has an even number of carbons, it makes it a lot more difficult to balance than if there's an odd number.
I thought I was looking at the same thing, and I
No.
wasn't. So okay,
If you have an odd number of carbons, it's a walk in the park to balance. If it's an even number, then it makes it more difficult. So I was just showing you the trick. Just multiply everything by 2, and you're good.
Got it.
Yeah.
Okay, thank you.
No problem. All right, so who wants to review something else? We can put
Maria
on
method, please.
anything you like. Dylan, what do you got?
The Maria method that you were just talking about. I want to know.
You want to know what it is? Okay. It was basically dealing with shapes. So who's got a Lewis structure they had problems with?
Number 4, letter F.
So what is that?
Worksheet number 4.
Okay, just tell me what
selenium chloride, trichloride with a positive sign, plus sign.
Sorry, what is it?
The number 4 of workshop.
No, just tell me what the molecule is.
Oh, selenium trichloride. With a plus sign.
Oh, with a plus sign.
Yeah.
Oh, okay. All right. So let me. Okay, so let's count up our total electrons. So how many valence electrons are we going to have here? How many does selenium have?
6.
Yep, it's right below sulfur and oxygen. So it's in group 6, so it has 6. And then chlorine, how many does chlorine have?
7 times 3.
7 times 3, that's 21. So that's a total of 27, right? Is that the right number?
No, plus.
No, because you have to
Oh.
plus a negative
So
one.
it's -1.
Minus
We have to
one.
take
That's
one
just
away.
one. Yeah,
right?
you take one.
So there's
So
really
yeah.
only 26. All right, so who's going to go in the middle, selenium or chlorine?
Selenium.
Selenium, right, lower electronegativity. We haven't really learned this, but electronegativity goes down as you move to the left. So we pretty much know that, right? Because the electronegativity gets higher and higher and higher until you get to fluorine, and it's the highest. It also goes down as the atoms get bigger, which makes sense because
The atomic radius gets bigger.
exactly. So, selenium is much bigger than oxygen. It's the same number of electrons in its outermost shell, but they're really far away. So the nucleus can't pull on them nearly as well as a smaller atom can. That's why fluorine is so damn electronegative, because it's really, really small. So you get like a really big element like iodine, and iodine. Now I'm saying it. Iodine is much bigger. It's huge. And so it pulls on those outer electrons a lot weaker. And so electronegativity goes down as the atoms get bigger. So selenium is a lot less electronegative. So we put a chlorine here, and a chlorine here, and a chlorine here. And we put our 1, 2, 3 bonds to start, right? So how many electrons do I have left?
20.
20, right. So I've used 6. 1, 2, 3, 4, 5, 6. So I got 20 left. So I decorate the outside with my 20. So 1, 2, whoops. Wait. Here we go. 1, 2. What? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I have 2 left. So if I have electrons left over,
Put
where do I
another
put 'em?
bond, right?
Hmm?
Put another one, right? I like it's like there's like 2 lines that make a double bond, right? From one selenium to
Oh, slow
chlorine.
down. I have 2 electrons left. So where do they go?
Selenium.
Oh,
They go in the middle, right? They go in the middle. So I put them here. So they go in the middle. So now I have none left. So now we check and see what the charges are and whether everybody has an octet or not. So let's look at the chlorines. All the chlorines are the same. All the chlorines have a bond and 1, 2, 3, 4, 5, 6 electrons around it. So did they all have an octet of electrons?
Yes.
They do, right? Because they have 2, 4, 6, and then a bond, shared bond, they can claim for a total of 8. So they're good. And what about the selenium? How many, does it have a full octet?
As with the 2 electrons and then the 3 that it shares with chlorine.
Yes.
It does,
No.
right?
Oh.
1, 2, 3, 4, 5, 6, 7, 8. So selenium has a full octet as well. Now let's check the charges. And this is something that I blame myself for not having taught very well. Let's look at the charges. So there's a difference between having a full octet and having enough valence electrons, like having the same number of valence electrons in the molecule as you had as an atom. So let's look at the chlorines. So the chlorines, for valence electrons, they can claim all of their lone pairs because they're their lone pairs, and they can claim one of the electrons in a bond. So they would have 2, 4, 6, and 1 makes 7. How many valence electrons does chlorine normally have?
7.
7, right? So fine. So none of the chlorines have a charge, plus or minus. But let's look at selenium. How many valence electrons does it have? Well, it has those 2, and it's got 1, 2, 3 more. So each atom claims one of the electrons it's sharing with the other atom as a valence electron, because that's what a valence electron is, right? It's an atom, it's electron you're sharing with another atom. And so you don't get to claim both of them as valence electrons. You only get to put as many electrons as you're sharing. So selenium is sharing 3, and it has 2 for itself, for a total of 5. How many valence electrons does selenium have as an atom?
6.
6. And it only has 5 as a member of this molecule, for a difference of +1. And so there's a charge, and it's on the selenium. So that's where the charge goes. That's where the charge comes from. It's on the selenium in the middle. So now we want to figure out what is the shape of that, right? So let's go back. So we got selenium, 2 electrons, and chlorine, chlorine, chlorine. So here's where we use the Maria rule. So we're going to, how do we figure out what the shapes of molecules is? What formula do we use? Do we remember?
AXE.
That's right. We use the Axe body spray rule. So AXE. So who's our central?
Selenium.
Selenium's our central atom. So remember, when you use the Axe body spray rule, we're only interested in the central atom. We do not care how many lone pairs the chlorine has, or any other atom bound to it. We're only interested in the bonds and the lone pairs of selenium and selenium only. Okay, so so X stands for bonding regions. And the Maria rule is don't bother thinking about bonding regions. How many atoms is selenium bound to?
3.
3. See, the genius thing about that is you get the same answer. Now, if there is a double bond or a triple bond, it doesn't make any difference. The only question is how many atoms is it bound to? And the answer is 3. So then you don't have to think about, regions in space and all that kind of stuff. How many atoms? 3. How many lone pairs? So E stands for electrons and lone pairs. How many lone pairs does selenium have?
1.
1. So then take out your sheet. Hopefully you've printed out your sheet or have it on your phone or something that I put in Canvas that has all of the shapes in it. And you just look up AX3E1. And what is that?
Trigonopyramidal.
Yep. So that means it's tetrahedral in shape, but it's not a full tetrahedron. That means it's got 4 different spaces where there's electrons, but one of them is only a lone pair. So what this would look like is, it's going to look like this. So we got our selenium here with our lone pair on the top, and then our chlorines are going to look like this. One coming out and 1 behind. So it's basically going to look like ammonia. It's the same sort of shape as ammonia. So next question. So that tells you what the shape is. Is it polar? How do we determine whether or not it's polar?
Well, the electrons on selenium would be slightly unbalanced compared to the other.
But that's not really how we determine polarity.
That doesn't have to do with the electronegativity, and since
Mhm.
chlorine is higher than selenium, and all 3 are pointing in 3 opposite directions, wouldn't that make it polar?
We need to
I would
write,
say it's balanced.
we need to figure out the bond dipoles first. We always figure, so remember, dipole means distribution of electrons. Are they even or are they uneven? If they're uneven, then you have a dipole. You have something slightly positive and something slightly negative. So which one is more electronegative? We figured out that's going to be the chlorine. So remember, when we draw a bond dipole, we draw it like this, pointing at the more electronegative element. So which direction am I going to point my bond dipoles? Toward the selenium or toward the chlorine?
Towards chlorine.
Towards chlorine, right? This little positive sign basically indicates which one is going to be slightly more positive. And the arrow points to the one that's going to be slightly more negative. So if we look at this, now we know what the bond dipoles look like, but we still don't know whether or not the whole molecule is polar. Now we need to see, do these bond dipoles cancel each other out? Or when we add them together, do they make a larger dipole pointing in a direction? So the fact that this lone pair is there means that these bonds are not on a plane. Remember, this is a tetrahedral shape, meaning that this bond and this one and this one are all pointing down, because the shape is going to look like this, all pointing down with your lone pair on the top. So if they're all pointing down, does that mean they add up together or do they cancel each other out?
Add together.
They add together in a pretty big way. Yeah, so when I would make the whole bond, the whole molecule dipole, it's going to point down and away from the selenium. And that makes sense because they're all pointing down and away. Now the difference, if it was planar, if this was boron, for instance, boron only makes 3 bonds. So if that was boron trichloride, that would look like 1, 2, 3. That would be a planar molecule because we will look at the AXE on that one. Boron's a central atom. It's bonded to 3 other atoms and it doesn't have a lone pair. That's a planar molecule, meaning that each one of these now are exactly 120 degrees away from each other and pointing in exactly opposite directions. So when we add these together, this one, and this one, they cancel each other out and it is non-polar. So just that one little lone pair makes the whole difference between the bonds being on a plane or being shifted down. If they're on a plane, they cancel each other out. If you push them down, it makes it polar. Does that make sense to everybody? The shape is really, really important. I mean, we're going to learn that basically there's only, I mentioned this last night, there's only basically 2 things you need to think about is shape and charge. That's everything that molecules have going for them. If we can figure out.
Sorry. So for nonpolar, it means that it's symmetrical.
Usually,
Like
yes. Yeah. Almost, that's right. Almost all nonpolar molecules are symmetrical.
Like there's an even distribution
Exactly.
all around.
Yeah, like CO2. It's the classic one. So so that is AX2E because carbon's bonded to 2 elements, and that is linear. So I've got 2 dipoles, one pointing in that direction towards the oxygen because it's more electronegative, and the other one pointing in that direction because it's more electronegative. But those are equal in size because the difference in electronegativity between this carbon and this oxygen is exactly the same as the difference between the carbon and the other oxygen. So these arrows are exactly the same size and pointing in exactly opposite directions. And so they cancel each other out. And the same would be true if they're both pointed at each other. They'd cancel each other out too. It's only when they're bent in space, when you have like bent molecules that aren't symmetric, they tend to be polar. That's a really good point. That sort of makes it easier to think about. Symmetrical molecules are almost always nonpolar.
So I have a question then.
Mm-hmm.
So when we're drawing the Lewis structure, so the difference for selenium in letter E is that you want to make sure the amount of valence electrons for selenium matches what's on the periodic table, but for letter F, because there's that plus charge, it's whatever you create for the Lewis structure, and then you have to add in what the charge is. That's the difference, like when you're drawing it.
Oh, so you see if I could,
like you see how for letter E it's
well,
SEF6, and then for this one it's
SEF6, right, is going to be different because you want to do that one because that doesn't have a charge, right? SEF6 doesn't have a charge.
Yeah, I think that's
Right.
where I want to make sure I understand, because like, or even like for letter H, right? Because there's a charge there that your structure is going to look a little bit different because of the charge.
It just means that if there's a negative charge somewhere, it means one of those atoms is going to have one more valence electron than it normally does. And if there's a plus charge, it just means one of those atoms is going to have one less valence electron than it normally does. And then you just have to figure out which one it is.
Can we do this one together?
The SEF6? Sure.
Sure.
All right. So pretty
Sorry
sure.
to interrupt,
Go
but
ahead.
for that last problem, based off of the structure, would it be polar or non-polar?
Which one are we talking about?
Selenium trichloride with a plus
Oh,
cation.
this one?
Yeah, the one that we just did.
That was polar because it had because of its shape. It was not symmetrical. It had a lone pair on one side and like 3 chlorines, well, like a lone pair on the top and 3 chlorines on the bottom. So not symmetrical, polar.
Okay.
Yeah.
And Professor, you want us to place the plus charge at the center, like the selenium part?
If that's where it's supposed to go.
Okay.
Yeah. Or, I mean,
The bracket one? you
we
mean?
haven't really talked about resonance forms. There's sometimes the charge can be on either. They can be on one atom or the one next to it. And I won't give you any of those. We'll deal with
Okay.
that. We'll deal with that later. But in this instance, chlorine never has a positive charge, ever. So it's bound to be on the selenium. But if you can't figure it out, you can always just put a bracket around it and put plus. So that's fine, because basically I'm asking you for the shape, right? So as long as you get the Lewis structure and the shape correct, the plus is just basically there to tell you how many electrons you should be using.
Okay, thank you, Professor.
Okay, all right, so we want SCF6. Okay. So 1, 2, 3, 4, 5, 6, right? Nope, 6. So how many total electrons should we have? Total valence electrons for
48.
SEF6. Oh, a lot more than 28.
48. No, I said 48.
Oh, 48. So fluorine's got 7 and there's 6 of them. That's 42. And selenium's got 6 for, 48. That's a bunch. So we'll just start by putting them around the outside. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oh, how many have we put in bonds already?
12.
12, right? We've made 6 bonds, we put in 12. So we're left with 36. 2, 3, 4, 5, 6. That means 6 on each of the 6 fluorines. 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And we're done. So that is 6 times 6. No electrons left. So let's check and see if everybody has an octet. So the fluorines, do they have an octet of electrons?
Yes.
They
Yes.
do, right? They have their 6 electrons in lone pairs, and they each have a single bond for a total of 8. So they're all good. And how many total electrons does selenium have?
12.
12. Selenium's got 12. Is that allowed?
Yes.
It is. It's totally allowed because selenium is actually in the 4th row. So selenium has S, P, D, and F orbitals. So selenium's got a ton of room for extra electrons. So that's not a problem. But let's see if it has, so it has an octet plus. So that's not having enough electrons is fine. But let's see if it has a charge. How many valence electrons should selenium have?
6.
And how many does it have?
It has 6.
It has 6, right? It has 1 from each of these bonds, so it has 6. So selenium is just super, super happy. It has 6 valence electrons and it has full octet plus. So selenium's
So
good to go.
So anything that's in the 3rd and 4th row, because they have more orbitals, it's okay for them to have an abundance of valence electrons.
Yep.
Or not, or
No, total
yeah,
electrons.
total, yeah.
Yeah, we still have to pay attention to the valence electrons to see how many, see if there's a charge. But for instance, sulfur has 6 valence electrons and often makes 6 bonds. Phosphorus has 5 valence electrons and often makes 5 bonds. So, and the same goes with the selenium and, with 6. They often make 6 bonds. So now it's just a matter of trying to figure out what the shape is. So the shape is going to be determined by the Maria rules. And so, and our Axe body spray. So as far as AXE goes, so AXE, selenium is our central. How many atoms is it bonded to?
6.
6. And how many lone pairs does it have?
0.
None. So we look up, what's the shape of AX6?
Octahedral.
Octahedral. So what that looks like is selenium, and we have a fluorine on the top, and we have a fluorine on the bottom, and 1, 2, 3, 4 fluorines around the outside. So this is these go behind, and these come out. So is this going to be polar or non-polar?
Non-polar.
Non-polar, yeah, because we don't even have to make the bond dipoles because this is completely symmetrical. It's octahedral, so it's symmetrical, and this is, in fact, selenium hexafluoride is a gas. And you can actually turn something as big as uranium. So uranium, you can turn into a gas by making uranium hexafluoride. And in fact, that's how you enrich uranium, by spinning it at a very, very high speed. And the slightly heavier, not less radioactive uranium will spin a little bit further. And the slightly lighter uranium-235, which you make atomic bombs out of, goes a little bit less. So you can actually turn a molecule as big as uranium into a gas just by putting 6 fluorines around it and making it octahedral. All right, any other things you want to look at?
I have a question.
Sure.
When I was completing the section just previous to this,
Mhm.
it was question 4 where we had to decide if it was going to be ionic or covalent.
Okay.
And in the reading, I read that covalent is typically a metal and a non-metal. Ionic is non-metals. How do the metalloids fit
Other
in?
way around.
Okay, right. I'm sorry. Yeah, I
Yeah.
flipped it. But how do the metalloids fit in, and how do we know which one it would be if all we know is that it's a metalloid?
Metalloids are typically make covalent compounds too. So when you
Okay.
see things with like silicon and the other classic one, arsenic and antimony. Antimony is a little more metallic than the others, but yeah, they generally make covalent. Yeah, they're sort of in a special group by themselves, but they generally make more, because the sort of the dirty little secret is there with bonds. Bonds can be ionic or polar or non-polar, right? But notice, I mean, if you read the book, there's sort of like there's some wiggle room there, right? There isn't like this bond is just ionic or this bond is just polar. Sometimes they can be a little bit of both. So basically, you know, even covalent bonds can have some ionic character to them. If the difference in electronegativity is enough, those bonds, which are covalent bonds, can have ionic character to them. So really what we want to break down is what's the difference in electronegativity between them. But really, when we look at whether or not it's a ionic compound or a covalent compound, just look and see if it's metals. If there's a metal in it and a non-metal, that's going to be ionic. And if there's 2 non-metals, that's going to be covalent. That's pretty much the short and easy rule to that. Just like everything, it gets a little more complicated if you look at it more closely, but just for now, all we have to worry about, if there's a metal in it, it's going to be ionic, because that means it's going to be a charge. Metals are going to give away electrons and non-metals are going to take them. That means it's going to be a charged compound, ionic compound. All right, anybody else? And we're good to go. Oh, so I want to point out, so tomorrow, test is going to be on a PDF. And if you can't print it out, don't worry. Just write down the answers on a separate piece of paper and submit that. Okay, so if you can't print it, or if you can't, you know, if you don't have the fancy pad that some of you seem to have, some of you Bing users have, if you can't write directly on it, on your tablet or whatever, yeah, just get a blank piece of paper and just write the answers down. Don't bother writing the questions over again. I know what the questions are. Just write the answers and show your work. And then just take a picture and just submit it. You'll have 3 hours. So the first couple of questions are multiple choice. So if you're, but you still have to show your work for those. If there's calculations, any calculations that need to be done, you have to show your calculations. If there's unit conversions, you need to show your unit conversions. Stuff like that. So even on the multiple choice, if there's calculations you need to do or unit conversions, you need to show them, like write it next to it. So if you're doing it on a blank piece of paper, like, 1C, and then show what your calculation is next to it, okay? And then, so there'll be, I think there's 10 multiple choice, and then 4 like written answers, and then there's a evil bonus question at the end, if you have time. I usually put evil bonus questions at the end.
Is bonus question extra credit?
Yes.
How many questions are there? I'm scared.
I think it was 10 multiple choice and 4 written, and then the evil bonus. I think.
Oh my God. Sorry. But like,
dude, you got 3 hours.
3 hours. Yo, I could. Oh my God.
Yeah,
Thanks.
usually my other class would only have 1 to do the same amount of work. So don't, you're getting 3.
Yeah, you're awesome. You know that? Yeah.
Totally awesome, of course. I know that.
No, you
just don't
gotta
get
do
to
the
give all the
Mr. E.
questions.
You gotta do the Mr. Burns evil laugh. Excellent,
Excellent. Yes. So any other things you want to review before we wrap it up?
So Professor, do we go to Chem 101 for that, or we can go straight to?
Oh, it won't be
just
on
go
Chem
to-
101. I'll release it on Canvas.
Mhm.
And so it'll be an assignment. It's right now, you'll see it, it's an assignment on Canvas. So it starts at 7 and then it ends, and I think you have like 10 minutes as a grace. If you like, if you take the whole 3 hours to finish it, you still have 10 minutes to submit it. But I would recommend doing the review on Chem 101. I think about 17 or 18 of you have done the review there. So good for you. That's a good place. Review these questions, and remember, I gave out a guide for review questions in the chapters. Not all of those review questions in the chapters you'll be responsible for, so don't freak out. If there's some of those questions that look completely new and frightening, we won't be doing those because we didn't cover everything in every chapter.
Thank you.
We don't have to come to Zoom at all, is that correct?
I will be here. I will be on Zoom to answer questions. So I'll be here. So I'm sure you're gonna have some questions. I'm gonna double check to make sure I didn't make any stupid mistakes like I did here tonight. I can't guarantee that I won't, but I'll, just because I know students always have questions during a test, like, what the hell does this mean? What the hell does that mean? Why are you doing this to me? Those sorts of things. So I'll be here to answer those.
And then Thursday is canceled since we're meeting on Wednesday.
Right.
Okay.
So I'm going to be using the office hours. I'm going to put this in an announcement tomorrow. I'll be using the office hours link.
So then the lab that's due on Thursday, I mean, we could still submit it late because honestly, I'm spending more time studying than.
Oh, totally.
Wow.
Yeah, I only take off points if they're like more than a week. If they're like a couple days, I don't really worry that much about it. If they're like a week or 2 weeks late, then I start to get concerned.
And then I was wondering, just in future, so like the office hours when we do come on Mondays, is there, I don't know, like can you record those, or is that preferential not to because you want people to go? I'm just wondering, just because I know,
yeah,
because I work, so it's hard sometimes, but it's honestly like
I see what you
yesterday's
mean.
was so
Yeah,
helpful.
yeah, I see what you mean. Yeah, I mean, if we're doing, I should have recorded the one on Monday because we did do some review,
or at
so,
least before an exam review, whatever that
Yes.
office hours before
yes,
that.
I will do that. Yeah,
I'm just
that was-
worried I'm
that was
not
my
always
bad.
going to be able to go. Thank you.
No, I totally understand. No, I should have done that. I should have thought of that.
I'm probably gonna get an A. Wait, it's gonna be hard, isn't it? It's gonna be hard and tough, right?
Oh,
Oh wait, oh yeah,
That's what
because it's
you
all on the
say.
workshops. Wait, it's gonna be on the workshops.
No,
We're all
you
chilling.
say it's not hard, but you're a chemistry teacher, okay? Of
Right,
course
so-
it's not hard for you.
So I'm evil. Well, hey,
And you admit you're
Oh,
evil.
and he makes
I
the
got-
So it's
questions
gonna be
evil.
hard.
Oh my lord.
I was getting my own questions wrong earlier tonight. So,
Yo, that must have said something, dude. This is gonna be the hardest test of my life.
Can you go over some of the Lewis structures for some of the other problems on the worksheet
Oh,
4?
sure.
I'm pretty sure I got the structures right. The issue for me was figuring out whether it was polar or non-polar.
Oh, okay. So which one are you interested in?
Phosphorus, tetrachloride was one.
Mhm.
Uh,
Is there a
oh,
charge?
no,
on that?
no, CL5,
Yeah,
Petra.
I was gonna say, yeah, that's
Yeah, I said Petra.
okay.
And then there's PF6 with a negative charge. And then there was PO4 with a -3 charge.
Oh, phosphate. Yeah, that's that one.
Yeah.
That one's a killer. Yeah, these two are pretty straightforward. So 1, 2, 3, 4, 5. Yeah, so this is just basically you're done. That's the structure. So it's
So
just
is it-
AX5.
And then it's a trigonal bipyramidal. So and I don't know if this matters, but the bond angle is 90 degrees for AX and 120 degrees for EQ.
Yeah, so what that means is
So
what that shape looks like actually is, let me erase this. So that shape looks like this. So it's got, let me just erase this. So the phosphorus is in the middle, and you have one chlorine pointing up, one chlorine pointing down, and then 3, one out, one back, and one in plane. And so this is, I should have drawn that a little better. More like this. There we go. So these angles are 90, and these angles are 120. This is called an axial bond, and these are circumference. These are around the middle, equatorial, equatorial. So this is also a symmetrical molecule.
yeah, that's what I was.
Yeah.
That's what I was thinking. What was that they all point at the kind of like a circle, and because of that, it should be
Yeah, it's going to be symmetrical, and so it's going to be nonpolar. And the difference with PF6 is that now phosphorus is connected to 6 fluorines. And phosphorus now has how many valence electrons? 6, right. It's got 1, 2, 3, 4, 5, 6. So how many does phosphorus normally have as an atom?
5.
5. So it normally has 5. Now it has 6. So it has a charge of -1. So that phosphorus in the middle is negatively charged.
And so since it doesn't have any lone pairs, it's an octahedral, and the bond angle is 90 degrees.
Yep.
And since they all point at, the fluorine is the one with the higher electronegativity.
Yep.
Would that also make it nonpolar?
It's also nonpolar. Yeah, it's hard to believe, but yeah, it's actually an ion that's nonpolar. Such things exist. Yeah, because you just have to look at the distribution of charge. If, as someone earlier pointed out, if it's symmetrical, if it's completely symmetrical in every way, it's nonpolar. So all this would need to do to make it polar is just change one of these atoms. If we just change change that fluorine to a hydrogen, and it's now polar. Because now it's not symmetrical anymore.
Oh. Because they'll be pointing towards fluorine, but hydrogen would be kind of longer.
Yeah, so all of these dipoles will be pointing towards it, but this one will be pointing in the opposite direction. And that screws up the symmetry. And so now it's polar. So just swapping out one atom changes it from nonpolar to polar.
So does that mean phosphate with the -3 charge would be nonpolar as well?
Sorry?
The other one that I had problems with was phosphate with -3 charge.
Oh, let's have a look at that. I think
kinda
we did
had
that. I think we
difficulty-
did that one last night, didn't we? Phosphate?
Mhm. We did this SO3 -2.
Oh, sulfite. Yeah.
Yeah.
Phosphate's a classic one. So. All right. So how many total valence electrons here?
32.
So oxygen's got 6, and there's 4 of them for 24. Phosphate's got 5. And we've got 3 more. So yeah, 32. 32 total. So we know phosphates or phosphorus is going in the middle because oxygen is much more electronegative. And there's 1, 2, 3, 4 of them. So we draw a single bond, 1, 2, 3, 4. That's 8 electrons. That leaves us with 24. So where do we put the 24 electrons? Where do we start putting them?
By the oxygen.
Sorry?
By the oxygen.
Yes, around the outside of the oxygens. 1, 2, 3, 4, 6, 12, 18, 24. I'm done. Now it's time to look at what the charges are. So how many valence electrons does oxygen normally have as an atom?
6.
6. And how many does it have? Each of them are all the same. So how many do they have in this structure?
8.
They have 8 total. How many valence electrons do they have?
Is it 7?
7, right. 2, 4, 6, and then 1 is 7. Yeah, we should have checked for octets first. I sort of jumped ahead. Yeah, so each one of them has an octet. The oxygens have a total of 8 with their 6 in lone pairs and a bond that makes 8. And phosphorus has 8 because it's has a total of 8 all in bonds. So everybody is an octet, so everyone's happy about that. But the oxygens have 1 more valence electrons than normal. And so they each have a negative charge. 1, 2, 3, 4. What about phosphorus? How many valence electrons does it have? Like electrons it can claim for its very own and nobody else.
Usually it's 5, but is it 4 only?
That's right. It usually has 5, but here it only has 4. 1, 2, 3, 4. So the charge on the phosphorus is +1. Now, the way this used to be taught, and I think probably still is most places, is that if you have a negative charge next to a positive charge, where are the electrons going to go?
One day
Towards the positive.
They're going to go toward the positive, definitely, because electrons are all, they have opposite charges. They want to get away from each other, and they want to go somewhere where there's a lack of electrons. And so a pair of these electrons, and it doesn't matter which pair, and it doesn't matter from which oxygen, one of those lone pairs is going to make a bond. Let's take this one. That's going to go there and make a double bond. So let's take that out. So now on that oxygen, how many valence electrons does it have? The oxygen with the double bond, how many valence electrons does it have now?
It has 5 now.
You sure?
1, 2, 3, 4.
6? Is it 6?
No, it has 6 because there's a double bond now. So it has 2, 4, 5, 6.
Oh, I didn't count the other ones.
Yeah, so it's got 6. So it's no longer charged. And that's what oxygen normally looks like, right? Oxygen normally has 2 bonds and 2 lone pairs. That's what oxygen normally looks like when it's in
I
a
think that's
molecule.
where I was confused, because then for the selenium tetrachloride, then couldn't you have a double bond for that one then? Or no?
No, because chlorine can't form, well, chlorine can form double bonds, but chlorine is so much more electronegative than selenium that it generally won't form double bonds. I think the only time chlorine will ever form a double bond is if it's, I don't think it actually ever does, come to think of it. No, I don't think it does.
So is it right to say that phosphates, sulfates, carbonates, they typically can have a double bond?
Yes, but so I'm just saying this is the way it used to be taught. So this now, how many valence electrons does phosphorus have?
Is it 10?
There's a total of 10, that's right, which is allowed because it's in the 3rd row, so it can break the octet rule. So how many valence electrons does it have?
5.
5, right. So it's got 1, 2, 3, 4, 5, which is the number it normally has. So now there's no charge. So we've eliminated 2 charges, which is generally what you want to do when you're making a molecule. You want to reduce the total number of charges as much as possible, especially if you have a negative charge right next to, like adjacent to a positive charge. Those two will generally cross each other out with a double bond. So this is what the phosphate would look like. We used to think would look like this. So there's a negative charge in this oxygen, a negative charge in this oxygen, and a negative charge in this oxygen, and that makes your PO4 -3.
Okay, because I did draw it with one of the oxygens double bonded. And but as you were starting this problem, I thought I was wrong because
Nope. But let me go back and say what we think now, just based on some research from like a couple of years ago, is we think phosphate actually looks like this. Negative, 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 positive. So group, I think I can't remember exactly where they were, somewhere in Scandinavia, I think, did some calculations to determine how big these bonds would be if there was a negatively charged oxygen adjacent to a positively charged phosphorus. And so the computer told them that the bond lengths would be the same as the bond lengths we see now, rather than 3 single bonds and a double.
so if on a test we drew it like as a double bond for one of the oxygens, will we be marked wrong for that?
No, because that's the way it was taught for like 100 years.
Oh, okay.
No, it was taught that it would look like this. And that there's actually, so this double bond could be on oxygen 1, it could be on oxygen 2, 3, or 4. And so what we haven't really learned is that there actually isn't a double bond on any of them, but it's sort of like an average of a double bond between all of them. So we say instead of there being a double bond on this one and singles on the other, we actually have what's called a bond order of 1.33 on all of them. Which sounds weird, right? It's basically 1.20, 5 bonds divided by 4. 5 bonds divided by 4 places to put them. Because what actually happens is that these electrons right here in that double bond actually move around and around and around and around. So we get an average. But I'm getting ahead of myself. You can draw it either way.
Okay.
Draw it either way. This is the accepted way. This one over here has been the accepted way for 100 years. We'll just leave it like that.
And so since it forms 4 bonds and there's no lone pairs, that would make it a tetrahedral. And because it's 4 equal places.
It's not equal though, right? Because this is negative. These 3 are negative, and this one isn't. So it is not. So you would say it's polar.
Oh, yeah. I mean, I got the Lewis structure right, but then the polar versus non-polar, that part messed me up.
Yeah, they're not all identical. I mean, they actually are, but according to the Lewis structure, they're not. So, yeah, you're free to say it's polar. Yeah, if you take like really advanced chemistry, you'll learn about like weird stuff like that. but this is an introductory chemistry class, so we'll just deal with this. Yeah, because one of the things nature loves is symmetry. And so this molecule over on the right is symmetrical. And symmetry is preferred above almost everything in nature and
For the
chemistry and
exam, is it
mathematics.
possible to use notes other than the reference sheet?
Notes other than what?
Other than the reference sheet you gave us and the AX work.
No, that's it. That's what you're allowed. Yeah,
Oh.
the cheat sheet with a periodic table. Yeah, the table of shapes, electronegativity table, polyatomic ions, and all of the. If I don't tell you what the unit conversions are, I may just give the unit conversion right on the test, so you don't have to look it up. But if it isn't on the test, yeah, the unit conversions are on that same cheat sheet that you should have printed out by now, or somewhere you can find easily.
And there's a few other Lewis structures I had trouble with regarding the practice problems. Silicone, SiS2 was one.
Mm-hmm.
And then there's SeOF2 and then C2H2. Those 3.
C2H2. And what was the other one?
SeOF2.
Okay.
So I was wondering if you can do them because I have really hard time.
So this one is fairly straightforward. So that is just written as carbon, carbon, hydrogen, hydrogen. And it has to be that way because hydrogen can only form one bond.
I thought maybe the carbon had to be double bonded.
Oh, no, it's more than double bonded.
Oh,
It's
okay,
actually
sorry.
triple bonded.
Oh,
But I'm saying that's the order that the atoms,
okay, right.
because hydrogen has to be on the outside. We can never
Right.
put it in the middle
Oh,
of anything because it only forms a single bond. So the order of the atoms has to be this. So we have a total of, 2 times, carbon has 4 times 2, and hydrogen has 1, 2. So that's a total of 10 electrons. right? And we've used 1, 2, 3 sets in bonds. So we only have 4 left. So I put 2 electrons here and 2 electrons there. So what am I going to do? Does either of those carbons have a full octet?
No.
No, they each have 6, right? 1, 2, 3, 4, 5, 6. So they're going to have to share one of those lone pairs. So one of the lone pairs goes in the middle. And now we're left with a double bond. But the problem with this is that this carbon still has only 6 total electrons, while this carbon has 2, 4. This one now has too many. There's a total. No, this one has 8 as well, but it has too many valence electrons. It has
So
one.
triple bond?
Yep. There's 1, 2, 3, 4, 5 electrons, valence electrons. That's too many. So that lone pair goes into the middle as well. And you're left with this. Now both carbons have 4 bonds and no lone pairs, which is typically what carbon is going to do. Have 4 bonds and no lone pairs, almost always, like 99% of the time.
Oh, and then the angle would be 120 degrees then, because that was another part of the question.
Nope. This is, so how many?
Oh, wait. Oh, I mean, 109.5 degrees.
Nope. So let's look at the carbon. How many, each carbon, how many atoms is it bound to?
Which carbon are we supposed to look at? Because both of them are the center, right?
Both of them are the same. So we can look at either one.
Yeah.
2, right?
Okay.
Each carbon is bound to only 2 other atoms, another carbon and a hydrogen. So this carbon is bound to only 2 atoms, this one and this one. And the same is true for this one. So they're both AX2, E0. That is linear.
Oh.
So that's a linear molecule. The bond angle is actually 180 degrees.
Okay.
So if you were to make that, if you actually make that as a model, you could just look right down it's completely linear. And that molecule is actually acetylene. You've probably heard of acetylene, right? Acetylene gas.
No, actually, I never heard of it.
And acetylene gas burns very, very hot. That's why you use it for welding, for like cutting steel and that. It's because it takes a lot of heat to break this triple bond. It takes a lot of heat to break that triple bond. And so by burning it, it burns very, very hot. That's the only way it'll burn. It burns at a very high temperature because of the amount of heat it takes to break those bonds.
Why are covalent bonds considered the strongest? I mean, if you compare the 4, you know, there's covalent, there's ionic, there's hydrophobic, and then there's hydrogen bonds. Why would covalent be considered the strongest one of the 4? I know that there's a lot of energy.
No, they're not. Ionic bonds are generally stronger.
Oh, really?
Yeah. It takes like to melt like a very ionic compound with like a lot of charges in it, melt at extremely high temperature. Like I think calcium oxide melts at like something like over 3,000 degrees or something. So yeah, it depends on what your definition of a strong bond is.
Oh.
Yeah. All right, so SeOF 2.
Yeah.
So does it say which one is the central? I mean, it's going to be selenium, but so it's going to have oxygen and 2 fluorines. So selenium is the least of the, has the lowest electronegativity, so it's going to go in the middle. So how many total electrons?
Uh, 12 plus 14, 26.
So 6, oops. 6 plus 6 plus 14, right, 26. And we've used 6, so 26, and we've used 6 in bonds. So we got 20 left. So 1, 2, 3, 4, 5, 6. It's 12. I've got 8 left. So I go 1, 2, 3, 4, 5, 6. Got 2 left, and I put them here. All right, so let's figure out, does everybody have an octet?
I know the fluorine goes.
Both fluorines do, right, because they have 6. Oops, I put too many electrons there. Oops. There we go. Yeah, so all both fluorines do, because they have 6 in lone pairs and 2 in the bond, so they're good. Oxygen's good. It has 8. What about selenium? Does it have an octet?
No.
You sure?
I counted 5, but maybe I'm counting wrong.
Well, total electrons. So remember, with total electrons for the octet, we consider all the electrons in bonds. So it does. So it's got 6 bonding electrons in a lone pair. So it has 8 as well. So now we consider whether there's charges or not. So the fluorines aren't going to be charged, because fluorine always looks like that, right? Fluorine always has 6 in lone pairs in a bond. Fluorine always looks like that. It never looks any different. So fluorine is not charged. What about oxygen? How many valence electrons does oxygen have?
Usually it has 6, right?
Yep, usually has 6. And how many does it have in this molecule?
8.
It is 8
7.
total, but 7 are valence, right?
Oh.
Because it only can count, basically valence electrons are just electrons that can count that belongs to it and it alone. So 7. So that oxygen has a -1 charge. And let's look at the selenium. How many valence electrons does it have?
Five.
Yep. 1, 2, 3, and the lone pair for 5. So normally it has 6 as well, but it only has 5. So that oxygen is a negative charge, and this selenium is a positive charge. So how do we avoid charges next to each other?
Change the bond.
How do we do that?
Double bonded oxygen with the CDN.
Right. So we take one of these lone pairs and we move it in between and make another bond. So that takes away a lone pair and gives another bond. So now the oxygen has 2, 4, 6 electrons. So that charge is now gone. And the selenium now has 1, 2, 3, 4, 5, 6 valence electrons, and it's not charged either. So that's what. So your final looks like this. So selenium, double bond, oxygen, single bond, fluorine.
And like, just as a, if we just write it like that, would that be correct in your eyes? Or would we have to all add all those like little dots, like for fluorine, we'd add.
If you're drawing a Lewis structure, you got to have
Yeah.
the lone pairs.
Okay,
Yep, got to have the lone pairs. And then as far as shape, selenium's bonded to 3 other atoms. It has 1 lone pair. So that gives it an overall tetrahedral shape. I think it's pyramidal. So it would be polar. I mean, it would have been polar anyway, but
is it because fluorine and oxygen are,
yeah, this isn't a symmetrical molecule. Even if it was planar, it wouldn't be symmetrical. So if it ain't symmetrical, it's
because the
be non-polar.
electronegativity of the fluorines both are higher than the oxygen rates.
Yeah, so if you were to draw dipoles, they would be pointing toward the fluorine and a smaller one toward the oxygen. Because fluorine's more electronegative. Right, anybody else have any other questions before we call it a night? Who do we have left?
Oh, you forgot the SiS2 one. Silicone disulfide.
All right. So, sorry,
S2.
S2. Okay. So we have silicon in the middle and sulfur on both sides, I believe. So how many valence electrons does silicon have?
4.
4. Just like carbon. And sulfur, how many does it have?
6 times 2, 12.
6, just like oxygen, right? For a total of 12. So 16. So 1, 2. And then that is 4 electrons. So we're left with 12. So where are we going to put the 12?
Where the sulfur would be.
So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So let's check and see if everyone has an octet. Pretty obvious silicon does not have an octet, right?
Right.
Looks fairly obvious because it only has a total of 4 electrons. That's a problem. So we need to give silicon an octet. So how are we going to do that?
Oh, would it be double bonded to both of the sulfur?
Yep. So this lone pair goes there. This lone pair goes there. And we get and you can see here now sulfur looks like pretty much what sulfur generally looks like oxygen normally looks like, 2 lone pairs, 2 bonds. And silicon, or silica, which is in the just below carbon, looks like carbon. It has 4 bonds and no lone pairs. So in actuality, this looks an awful lot like carbon dioxide. In fact, it's going to be exactly the same shape and have a lot of the same properties. So is it going to be polar or non-polar? Actually, what shapes are going to be first? So you look at the silicon, how many, so AXE, how many atoms is the silica bound to?
2.
2. And does it have any lone pairs?
No,
Nope. So what shape is that? AX2.
linear.
Linear, just like carbon dioxide. It is linear. And so is it polar or non-polar?
Non-polar.
Non-polar, right, because it's symmetrical. So just like carbon dioxide is non-polar, silicon disulfide is non-polar as well.